This is the second lecture on data compression. The previous lecture dealt with basic concepts related to data compression, as well as basic Huffman coding. This lecture looks at adaptive Huffman coding, as well as run-length encoding. Let's at this point very briefly recap the operation of the Huffman coding algorithm. So the algorithm constructs a binary tree, and it bases this tree construction on the probabilities of occurrences of symbols in the data that we are attempting to compress. Now, from this point on, we will assume that the data that we're attempting to compress is textual in nature, and in other words, the symbols are characters. Now, once we've constructed this Huffman coding tree, we then need to determine the encodings of the symbols that occur in the document that we want to compress. And we determine these encodings by means of traversals of the Huffman tree that we have previously constructed. Now, the obvious question that arises is, how do we know what the probabilities of these characters are? Well, one approach that we could use is we could treat the language that we're attempting to encode, for example, English, as a whole, and we can then calculate the average character frequencies for this language and then use these frequencies as probabilities. Now, what this approach would require is that we'd need a very large database of documents ranging from reference works to novels to short stories and poems to websites, and we then have to pass through all of these documents and compute the occurrences, the number of occurrences of these characters within these documents. So this is obviously a very cumbersome and probably incredibly time-consuming operation, and therefore it's probably not ideal to follow this approach. Additionally, we run into a problem when we're dealing with different kinds of documents. So let's consider, for example, the COS 212 textbook versus a novel like Harry Potter and the Philosopher's Stone. Now, what we would expect is that these two documents would be made up of text that consists of very different vocabularies. So, for example, in the COS 212 textbook, we would tend to see very technical terms which we wouldn't see at all in the novel. So what this then essentially means is that the character frequencies would differ between these two different kinds of documents, and a general overall character frequency that we've computed for the entire English language will not necessarily apply as well as it possibly could for each of these different kinds of documents. So a simple solution to this approach then is that we can calculate frequencies for the specific text that we are attempting to encode, and then we can send the corresponding Huffman codes in terms of the Huffman tree, as well as the compressed data to the receiver of our compressed message. The receiver would then be responsible for actually decoding this message somehow. And this is essentially the approach that we described towards the end of the last lecture. However, the text may be potentially very long, and we also now have to run through the text twice. So we need to run through the text once in order to compute the character frequencies, and then a second time in order to perform the actual compression. So this is obviously not very efficient. And additionally, dealing with the table of codes as well as the Huffman tree can be fairly cumbersome for us. So this leads us then rather neatly to the concept underlying adaptive Huffman coding. So what adaptive Huffman coding does is it runs through the text only once, and it generates codes for characters as we go. And initially then these encodings for our characters are very inefficient. In other words, they're very long encodings that require a lot of bits. However, as we then encounter more and more characters, the adaptive Huffman coding algorithm then learns the frequencies of these characters, and it then improves the codes for them by making them shorter where it's appropriate. So what this means then is through the course of the execution of the adaptive Huffman coding algorithm, the codes for characters will change. The receiver then will, of course, once again receive the encoded message, but the receiver will then reconstruct the same Huffman tree dynamically in exactly the same way that the sender constructed the tree. So then to decode, the sender and the receiver, very importantly, must agree on the alphabet that is used and the order that the characters that are encoded appear within this alphabet. The Huffman coding algorithm begins its execution with a Huffman tree that contains only one single node. Now this node then stores the entire alphabet that could potentially be used within a document that we need to compress, and we refer to this node as the alphabet node. The frequency of this node must be 0, and this is because none of the letters in the alphabet have yet been used in an encoding. So this is an example of what the alphabet node would look like. We can see that we have a frequency that we need to store, which is 0. And then we have a list of characters, which is the alphabet. And these characters must be ordered in a pre-decided way. Now, in a real-world application of the adaptive Huffman coding algorithm, we would typically have to encode the entire alphabet as well as probably numerals and also punctuation symbols. However, for the purposes of the simple examples that we'll be using within this lecture, we're going to assume that the entire alphabet consists of only the letters A through F. So what this means then is that the document that we want to compress can consist only of characters that are selected from this alphabet. All right, so then when we encode the text, we encode it letter by letter. And in other words, there is no pre-processing in order to find the frequencies of letters within our document. So as we then encounter letters and we encode them, then we move those letters out of the alphabet node into the rest of the tree. Now, there are two cases then that we need to deal with when we are encoding a letter. The first case is if the letter is still contained within the alphabet node, and the second case is if the letter is not contained in the alphabet node. In other words, the letter is somewhere within the rest of the Huffman tree. Now we'll be discussing each of these two separate cases individually in the upcoming slides, and we'll be discussing them in parallel with an example that we'll be working through. So the first case that we need to deal with is if the letter I is still contained within the alphabet node. So over here we have our alphabet node that we'll be using for the remainder of this example. And we also additionally have some input text over here, which is what we need to encode. We also have our encoding, which at this point is empty because we haven't yet processed any of the letters yet. So now we work through the letters one by one. So we start off with the first letter, which is A. So now what we need to do is we have to generate a code, and because this letter A does not exist within the rest of the Huffman tree, this code then must be based entirely on the position of the letter A within the alphabet node. So in other words, the encoding must somehow communicate the fact that the letter A is in the first position within the alphabet contained in the alphabet node. Now, there are many different ways that we could encode this information, but the approach that we will use for this example and the remainder of this discussion is as follows. So first of all, we start with the Huffman code of the alphabet node. Now, of course, at this point, the alphabet node is the only node within the Huffman tree, so therefore this portion of the code will be empty for the first character. But we'll see as we move through the example that there will be then bits within this portion of the code once we have additional nodes within our Huffman tree. Right, so following the Huffman code of the alphabet node, we then add a sequence of 1 bits, and here the number of 1 bits then corresponds to the position of the letter within the alphabet that is currently contained in the alphabet node. We then indicate the end of the code with a single 0 bit, which indicates then that the sequence of 1 bits has ended. All right, so let's look at some examples of this then. If we assume this is the alphabet that we're working with, the letters A through F, then the code for A, if we disregard the first portion of the code, which is the Huffman code of the alphabet node, would then be 1, 0. And the reason for this is that A is contained at the first position within this alphabet, which means then that this single 1 bit indicates the first position, and we then follow that with a 0 indicating the end of the code. In a similar fashion, if we are generating a code for D, which we've encountered for the first time, then this would be the code here. So we have 4 ones followed by a 0. And the reason for that is that the letter D within the alphabet is the 4th letter. All right, so this is relatively straightforward. And then we, of course, once we've generated this code, it then needs to be appended to the encoded bit sequence. All right, so let's look at our example over here then. We're trying to encode the letter A, and we see that the letter A is still contained within the alphabet node. So therefore, we need to generate a sequence of bits which indicates where A is positioned within the alphabet. So the first portion, the Huffman code of our alphabet node, is empty. We then have a single 1 bit, which indicates that the A is in the first position within the alphabet, and then we follow that with a 0. So now we've finished encoding the letter A from our input text. Next, we need to split the letter that we've just encoded out of the alphabet node. So we do this then by, first of all, within the alphabet node, moving the last letter to overwrite the letter that we've just encoded. So in our example over here, we will be moving the letter F, and we will be placing that in the position that A occupied previously, therefore removing A from the alphabet node. So this is exactly what we've done over here. We see now that we have F that is stored in the first location, and the letter A no longer exists within the alphabet. Next, we need to create a new node for the letter that we've just extracted from the alphabet node, and we give this, of course, a frequency of 1 because we've only encountered this letter once. So in our example over here, we now have a new node that contains the letter A, and its frequency is 1 because we've only encountered the letter A once within our input text. Then finally, we need to create a new parent node for these 2 nodes, the alphabet node and the new node that we've created. The left child of this new node is the alphabet node, the right child is the new node, and its cumulative frequency is, of course, 1 because the cumulative frequency is the sum of the frequencies of the 2 children, and those frequencies are, as we can see over here, 0 and 1. Right, so we then increment the counts in the new node's ancestors if there are any ancestors. At this point, the new node that we've created does not have any ancestors, so we don't need to increment any further counts, but we'll see an example of this set of incrementing operations as we move on with this example. Also note that the left and right branches of the new parent node that we've created are appropriately coded as 0 for the left branch and 1 for the right branch, just as we saw with the standard Huffman coding algorithm that we covered in the last lecture. Let's now look at the situation where we encounter a letter that is not contained in the alphabet node. So if we look at our example, we now move on to the second letter, and we see that we've encountered the letter A once again. And if we check the alphabet node, we see that the letter A is not contained within the current alphabet. What this then means is that the letter A must be contained somewhere else within the Huffman tree. What this then also implies is we can encode this letter using the standard encoding approach that we used with a normal Huffman encoding algorithm. So we basically then generate this encoding by starting off at the root node of the tree and traversing down until we reach the leaf node that contains the letter that we're encoding. And as we then traverse, we record for each branch that we traverse through, whether it's a 0 branch or a 1 branch. We then concatenate all of these 1s and 0s together, and then we add the encoding to our encoded bit sequence that we're generating. All right, so in our example over here, we then start off at the root node, which was added in the previous step, and we traverse to the right, and then we encounter the leaf node for the letter A. We see that we've only traversed then one branch, which is the right branch of the root node, which means that we then only add a 1 bit to our encoding, and that's then added to the encoded message, as you can see there. All right, so what you should notice at this point is that for the first letter A that occurred in our input text, we used an encoding of 1, 0, and for the second letter A, we used an encoding of 1. So in other words, our encoding is evolving as we see more and more characters. And what this will then result in is a more and more optimal coding as we see more and more characters, and as we get a better and better idea of what the frequencies for the various letters are through our input text. All right, so now we've finished with our encoding. What we need to do next is increment the frequency of the letter's leaf. And the reason that we need to do this is that we've encountered at this point a second A, so we now need to update our knowledge in terms of the frequency for that letter. So in our example over here, we can see then we've incremented the frequency for the leaf node containing the letter A from 1 to 2. Additionally, we also need to update the frequency counts for all of the ancestor nodes of the leaf node that we've just updated, and we do that all the way up to the root node of the tree. All right, so any frequency increment then may break the structure of our Huffman tree. So recall from the previous lecture that a Huffman tree should be, first of all, merging nodes that have a very low probability, and therefore nodes with a higher probability will occur higher up within the tree structure. All right, so if we then encounter a situation where the structure of the Huffman tree has been broken, we then need to repair the tree structure. So to do this, we will then link all of the nodes within the tree by means of a linked list, and the order that these nodes will be linked in is a breadth first, right to left order. So over here you can see by means of these green arrows, we've now linked the nodes in breadth first, right to left order. So we start off then at the root node, and then we move to its right child, and then to its left child. Now we need to then, through all of our changes to the tree structure, still then maintain and update this linked list structure as well. So this is another bookkeeping task that we need to take care of. So then as we update frequency counts within our Huffman tree, we need to maintain what's referred to as the sibling property. So essentially what the sibling property states is if the frequencies in the list are non-increasing, then the tree is a correctly structured Huffman tree. However, if the sibling property is broken at any point, then it must be restored, and we'll speak in a moment about how this restoration of the Huffman tree structure actually needs to take place. So in our example over here, if we then follow the green arrow, we see that the frequencies then in order are 1, 2, and 0. So in other words, we have a situation here where we have an increase in the sequence. In other words, our frequency value has increased from 1 to 2 and then to 0. What this means then is that the sibling property has been broken at this point, and an update to the tree structure is then required. So how do we go about restoring the sibling property once we've detected that it's been violated? So we use the linked list structure in order to do this. And within the linked list, we have the notion of blocks. So blocks are sequences within the linked list of nodes that all have exactly the same frequency. So if we look at our Huffman tree prior to the increment that we performed for the node A, where we incremented that frequency from 1 to 2, we then see that the linked list in order, if we record the frequencies, running from the root node to the right child and then finally to the left child, would then be the sequence 1, 1, and 0. So in other words, within this list of frequencies, we then have two blocks, which I've highlighted over there. So there's one block that contains two occurrences of the frequency 1, and one block that contains one occurrence of the frequency 0. Now we'll be working with the blocks prior to an increment to a frequency which we then need to correct. Alright, so within then our tree structure after the increment then has taken place, we can see that we have then our frequency list containing then our two blocks. And our first block contains the frequencies 1, 2, where we've updated this second frequency to 2, and our second block then contains 0 at that point. So now if we assume that the sibling property has been violated by a frequency update for node I. So in this example, node I is the node that contains the letter A. Then what we need to do is we need to swap I with the first node in its block, unless that first node is the parent of I. So in other words, we need to swap the node that has a frequency of 2 with the first node that has a frequency of 1. In other words, we need to swap the node for the letter A with this root node over here. But we see that this root node is the parent of the node that contains the letter A, which means that no swap needs to be performed at this point. So then we move on to the next part of the correction operation, where we then continue with frequency increments for all of the ancestors of I. So I being then the leaf node that contains the letter A, we then need to update the frequency for its parent node over here. So we update that frequency then. That frequency is the cumulative frequency, of course, for its two children. So we then just increment that frequency by 1, and so now it's been updated to 2. We can now see that if we look at the frequencies within our list, we now have this sequence over here. So we have a frequency of 2, followed by 2, followed by 0 if we follow our linked list in order. So in this case, we see now that we have no increase in frequencies in order. The frequencies either remain the same or they decrease, which means then that we have restored our sibling property. Now, what's important to note at this point is that several sibling property violations may be encountered as we work our way up towards the root node, and each of these violations will require then a separate correction each time. Now, in this particular example, because our tree is so simple, no further corrections are required because there are no further ancestors. for the leaf node containing the letter A, but we'll see as we continue with our example, there will be situations where we have to perform several corrections. We're now ready to move on to the third letter of our input text, so we move on to the letter F. If we check the alphabet node, we see that the letter F is contained within the alphabet, which means we first of all need to generate an encoding for the letter F. So to do this, we need to first of all generate the Huffman code for the alphabet node, and we do this by traversing from the root node down to the alphabet node. So the traversal path is highlighted in red, as you can see, and we traverse only along one left path, which means that we then have to add the code 0 as the first part of our encoding. Next, we need to include in our encoding the position of the letter F in our alphabet. And as we can see in the alphabet, F is the first letter, which means that we need to then add a single 1 bit to our encoding. We follow this 1 bit with a 0, which indicates the end of our encoding, and so our full encoding for the letter F is 010. So now that we've finished our encoding, we need to create a node for the letter F. First of all, we need to process the alphabet in the alphabet node. So we do this by taking the last letter in the alphabet, which is E, and we move that to overwrite the letter F and extract the letter F and then create a new node for it. So there we have overwritten F with the letter E, and then we create a new node for the letter F, and the frequency for that node is 1 because we've only encountered F once so far during our encoding process. Next, we need to create a parent node for the alphabet node and the new node that we've created. So we create a new node, and we have the alphabet node as the left child and the node for the letter F as the right child. The cumulative frequency is 1, which you can see makes sense in terms of the frequencies of the left and right child for that node. Additionally, notice that because the root node was the parent of both the alphabet node and the node for the letter F, it also needs to be the parent for this new parent node with the cumulative frequency of 1 that we've just created. Alright, so now we've created a new parent node. We now need to update the frequency of the ancestors of this new parent node. So this then only includes the root node, and we increment the frequency from 2 to 3. So the final thing that we need to do is to restore our linked list structure, which you can see is indicated by means of the green arrows over there. We don't at this point need to test to see whether our sibling property has been violated, because we are dealing with a letter that is contained in the alphabet node. However, if we check the frequencies in our list in order, we can see that we have a decreasing sequence of frequencies, which means we don't have any increases, and therefore we don't need to deal with any violations of the sibling property. We can now move on to the fourth letter of our input text. So we now consider the letter C. If we check our alphabet node, we see that C is still contained within our alphabet node, which means that we first of all need to generate an encoding for the letter C. So to do this, we need to determine the Huffman code of our alphabet node, and we do that again by means of a traversal from the root node down to the alphabet node. So over there you can see the traversal path highlighted in red. We traverse along two left paths, so therefore we have 2 zeros that are included as the first part of our encoding, and this is the Huffman code for our alphabet node. Next, we need to encode the position of the letter C in the alphabet. So we can see that the letter C is the third letter within the alphabet, which means that we need to then add 3 1 bits to our encoding. And once again, we then end our encoding with a 0, indicating that this is the end of our sequence of 1 bits. Right, so now we have completed our encoding. We now need to create a node for the new letter that we've encountered. So we do this once again by updating our alphabet. So again, then within our alphabet node, we take the last value in the alphabet, which is D, and we move it to replace the letter C that we are currently dealing with, and we remove C then from the alphabet as a result. So that's what we've done over there. Next, we need to create a new node, which we've done here. So we've created a new node for the letter C, and we've set its frequency to 1. Then, as the final step for this letter's encoding, we need to create a new parent node for the alphabet node and the new node that we have created. So the cumulative frequency there is 1. You can see again that makes sense in terms of the frequencies of the two children. And then we need to work our way through the ancestors of this new node all the way up to the root of the tree, incrementing frequencies as we go. So we first of all then increment the frequency of its parent from 1 to 2, and then we reach the root node, which we increment there from 3 to 4. All right, so now we've updated the frequencies. The next thing that we need to do is restore our linked list structure, which we've done over there, which you can see by means of the green arrows. And then again, we do not need to check for any violations of the sibling property. However, if we look at the frequencies within our list, we can see that we just have a decreasing sequence. There are no increases over the course of the frequencies within that list, which means that no corrections are required. So now we can move on to the fifth letter of our input text, namely the second C, as we've indicated over there. So again, we need to check our alphabet node, and we see that at this point C is not contained in the alphabet node. In other words, the letter C is contained in another node within our Huffman coding tree. All right, so we then need to generate a Huffman code for the letter C in the usual way, exactly as we've done before with the standard Huffman coding algorithm. So we trace then a path from the root node all the way down to the leaf node that contains the letter C, which I've highlighted in red over there. And if we then look at the paths, we can see that we have a 0 path, followed by a 0 path, followed by a 1 path. So this means then that the encoding is 0, 0, 1. All right, so now we've generated our encoding. Now we need to go about updating our frequencies. So we've now updated, as you can see, the frequency of the node containing the letter C from 1 to 2. What we now need to do is move from this leaf node where we have incremented the frequency all the way up to the root node, correcting frequencies as we go. However, each time that we update a frequency, we need to check to see whether the sibling property has been violated, and if it has been violated, then we need to correct it by means of a node swap. So if we then check our frequency list over here, we can see that the sibling property has been broken. We have a decreasing sequence, but at this point here with this 2, which corresponds to the frequency that we've just updated, we now have an increase, which is an anomaly, and that breaks our sibling property. So at this point, we now need to perform a correction. And what we do is we then swap this node where the violation has occurred, in other words, this node with frequency of 2, and we swap it with the first node within its block. So its block is this sequence of 1s, meaning that we need to swap it with the node for this first 1 frequency over here. So if we look at our green path, our linked list, and we move from the root node, then we can see that the very first one that we encounter is for this leaf node over here that contains the letter F. So what this means is we need to perform a swap between the node containing the letter C and the node containing the letter F. So that's exactly what we've done there. Of course, if there were any children under either one or both of those nodes, those children would swap with those nodes as well. So it's not a value swap that we're performing, we're actually swapping the nodes themselves. However, in this case, there are no children, so we just then swap the nodes directly. Right, so now we're dealing with C, where we've dealt with the frequency update, and now we need to move on to its parent. So this is the parent node over here. We've increased the frequency from 2 to 3, and now we need to check once again to see whether we have violated our sibling property. Well, we have. If we look at the frequencies within our list, once again, we've got a decreasing sequence, but then we have this anomalous increase over here, which corresponds to this node over here, where we increased the frequency from 2 to 3. So once again, we then need to perform a swap. We need to swap this node where the violation has occurred with the first node in its block. Its block includes this value 2 over here, so we're swapping it then with the node that has the frequency 2 over here. So in other words, that's a swap then between the node where we've just updated the frequency and the right child of the root node. Right, so we perform a swap there. Now notice here that the node with a frequency of 3 has children under it, and those children then swap with this node. So this entire subtree then moves to the right branch of the root node. The single node that contains the letter A moves to be the left child of the root node. So that's exactly what we've done over there. And again, you can see our linked list indicated by means of green arrows there. All right, so we will end then this example at this point. You can see that in our input text there are still 4 letters that need to be encoded. So this will be left as an exercise to use. So work through the remaining letters, encode them and perform updates to the Huffman tree structure according to the same procedure that we've done so far. All right, so this then essentially summarizes the encoding operation. Now, of course, the question arises, how do we perform decoding? Well, decoding is actually almost exactly the same operation as encoding. So again, we start off with just an alphabet node, and we then split nodes off from the alphabet node. The only difference is that instead of working from input text and generating encodings, we now work from encodings and generate input text. So in other words, we need to, from the bit sequence, figure out which node is being referred to. And if we determine that we are referring to the alphabet node, then we need to decode the bit sequence following that to determine which letter we're referring to. And if we don't, through our traversal, reach the alphabet node, but instead we reach some other leaf node, then we just simply decode that leaf node. The important thing to understand is that the decoding procedure requires us to maintain and update a tree structure. So as an exercise, once again for you, look at the algorithm for adaptive Huffman encoding. There is a pseudocode representation of that algorithm in the textbook for the course, and see how you would have to update that algorithm in order to allow a decoding procedure to successfully execute. So that concludes our discussion on adaptive Huffman coding. We will now discuss the last compression technique, which is referred to as run length encoding. Now, run length encoding is actually a very simple encoding scheme. It's definitely a lot simpler than Huffman coding and adaptive Huffman coding. However, it is used quite widely in practice. In fact, fax machines use run length encoding in order to compress the images that are sent from one machine to another. So run length encoding relies on the presence of what are referred to as runs in the data that's being encoded. And a run, very simply, is a sequence of exactly the same characters. So if we look at this character sequence over here, we can see that we have 5 runs. So we have a run initially containing 4 repetitions of the letter A, another run that contains 2 repetitions of the letter B, a run that contains only the letter C, a run that contains 4 repetitions of D, and finally a run that contains 2 repetitions of the letter E. All right, so instead of then storing or sending, depending on what we're performing the compression for, a full sequence of A characters, we could then encode this just simply as 4A. So the number 4 then indicates that we have a sequence of 4A characters, and the A indicates what the sequence consists of, in other words, the letter A. However, the question then that obviously should pop into our minds is, when would we ever actually see such text in the real world? And the answer, of course, is that we would be very unlikely to see this kind of text, for example, in a book or a reference manual. So as a result of this, run length encoding is incredibly inefficient for text. However, let's consider images. So images consist of a number of pixels, and these pixels are arranged in a rectangular structure, and the pixels have some kind of color value associated with them. The color value can be represented in a variety of different ways. A fairly common approach is an encoding of 3 values representing the red, green, and blue balance of the color for that particular pixel. So if we look at these images over here, for example, the image on the left of the moon, we can see that a large portion of the image is black, and there's also a very large portion of the image at the bottom that is a bluish color. So essentially what this means then is that we will have fairly long sequences of black colored pixels and also fairly long sequences of blue colored pixels. This lends itself directly to run length encoding. So if we then have a run of pixels with the same color, we can then indicate the number of pixels and then just simply the color value for those pixels. As long as the decoding approach then reads the pixels in the same order, so typically this would be then left to right and top to bottom through the image, then the image can be decoded. And the larger the uniform areas of color within the image are, the greater the level of compression is that we could potentially achieve. So how would we actually go about implementing run length encoding? Well, the algorithm for run length encoding is actually incredibly simple. We simply iterate through all of the letters in the input text from left to right, and then we encode each run with just 2 characters. So if we look at our example over here, this would be an example of what run length encoding would look like. So we have 4A over here, and that indicates that we have a run of length 4 of the letter A. In a similar fashion, here we have a run of length 4 of the letter D, and that would be represented by this 4D over here. All right, so what we see then in this example is that the first, second, fourth, and fifth runs are either compressed, in other words, they consist of fewer characters than in the original input data, or they remain the same length. So we can see, for example, that this first run of A's over here, we've used 2 characters to represent it, whereas in the original input text, we used 4 characters. In the case of B over here, we have 2 Bs. We've encoded that as 2B over here as a run length. We can see that the encoding consists of 2 characters, whereas the original data consists of 2 characters. So in that case, we haven't lost any data space. We haven't wasted any of our available data space, but we also haven't gained any by means of a compression. Right, what we see, however, in this example is that there's one exception, and that is the letter C, which, as we can see, occurs in a run of exactly 1 character. And what we've done here is we've actually then used 2 characters to encode the letter C, whereas in the original data we used only 1 single character. So in this case, we've actually then increased the amount of space that we've used. So this is obviously not an ideal situation, and a fairly simple solution to this is that we compress then only the runs that are long enough. So in other words, in the previous example, we would omit compressing the character C. Now what this of course means is that we have a mixture of compressed and uncompressed characters, so we need some way to tell which are compressed and which aren't. Now, a fairly simple way of doing this is by means of a special character, what's often referred to as an escape character, and this then indicates compressed runs. So for example, we might use the percentage symbol as an escape character, and then our encoding becomes the following. So we can see then that all of our run length encodings start with a percentage symbol. So over here we have a run of 4 A's. We have the percentage symbol indicating that this actually is a run that we're encoding. We see in the case of C here that there's no percentage symbol before it. So as we decode this and pass through it from left to right, we encounter then just C, and then the algorithm would know at that point that we are dealing with just the character C and not a run length. Right, so in this case, we have then not compressed the data quite as much as we did before because we have this additional escape character that we have to include in our encoding. Now, sometimes it's not necessary for us to include escape characters. For example, if we could assume that our data consists only of alphabetical characters and no numeric characters at all, then we don't need to include the percentage symbol because the numbers indicate both the length of runs and they also serve as escape characters. This, of course, depends on the kind of data that you're compressing, however, and this is then very context dependent. So what we see then in our encoding over here is we still have a situation where we have our runs of length 2, so in other words BB and EE over here, and they are encoded by means of the percentage symbols as sequences of 3 characters. So in this case, again, we've wasted space unnecessarily. So we can solve this once again in exactly the same way as we did for the run of a single character. We compress then only runs that are 3 or more symbols long. So in other words, then in this case, we would have 2 runs that would be encoded where compression actually takes place. This first run of 4 A's and then this second run of 4 D's. However, we can see that A, B, B, C, and then at the end of our sequence EE remain then uncompressed, and they're just represented as characters directly. Now let's consider a situation where we have 2 alternative sequences of letters. The first is in the form that we've seen before. So we have in both of these sequences 3 A's and 3 B's, but in the first case we have a run of 3 A's followed by a run of 3 B's. In the second case we have an alternating sequence of A's and B's. Now if we were to use Huffman encoding, then we would be able to compress both of these, and the reason is that Huffman encoding is dependent on the frequency of character occurrences. So in both of these cases, because the A's occur 3 times and the B's occur 3 times, this means that Huffman encoding will be able to then compress to the same level both of these sequences. However, would run length encoding be able to? Now, if we use the definition that we've just spoken about, then run length encoding would only be able to compress the first sequence over here. It wouldn't be able to compress the second sequence because we have no runs of consecutive characters that are all exactly the same. However, we can try to sidestep this by having runs that can consist of multiple characters strung together. So we could then interpret this sequence as a run of 3 occurrences of the pairs of letters A and B. Now, this is, of course, very problem dependent. It may make sense in one particular setting to allow for runs that consist of multiple characters, and in other settings, this may not be appropriate. So once again, this is very problem dependent. So finally, let us consider then binary sequences. Now, binary files consist only of 2 symbols, zeros and ones. So what this means is there's a much higher chance that there will be runs of zeros and of ones. And this means there's a lot of potential for compressing binary data then using run length encoding. But the question is then, how would we actually apply run length encoding to binary data? Now, we could obviously use a non-binary representation, possibly a text file, for example, and then just encode numbers that represent then the counts of bits. We could also potentially encode our numbers as bit sequences, but once again, how would we then tell those sequences apart from the data that we're actually trying to compress? So in order to use a more efficient encoding, we need to actually find some kind of way of representing an escape character in binary. So what I would like you to do as an exercise is think a little bit about this problem and try to think of ways that you could potentially represent escape characters so that one would be able to efficiently run length encode binary data. Right, so that concludes then our discussion on compression algorithms. In the final lecture of the week, we will move on to chapter 13, where we'll be looking at string matching.